Hi everyone, in this video I will continue discussion on the definitions and this point I will define velocity dependent um, function here and I will discuss about the given function. This is velocity dependent friction model. So this command that I am referring to, it's available in OpenSees and STKO environment, and it is used for simulation and modeling of the frictions. So this command is used to create an object that represents a velocity and dependent friction model, especially it is tailored for material like PTFE, polytetra fluoroethylene, sliding on a stainless steel surface. And there we have some values. This is mu slow, mu fast, and this is transition rate, right, from low to high velocity. So basically, if you go to the OpenSeas documentation and we study about this model, this friction model state that this command is used to construct a velocity-dependent function model object, and it's useful for modeling the behavior of PTFE or PTFE-like material sliding on the steel surface. So the first thing from the origination of this model, if I consider discussion on it, so this is the Constantino et al. 1999 model from which it is considered, and this required a friction tag, a unique friction tag, right? And then it's defined, it's required a coefficient of friction at low velocity and coefficient of friction at high velocity, as well as transition rate at, at which rate this model is changing and it's getting the maximum friction in this requirement. So for example, if we look at this behavior, for example, if it is velocity and then this is average coefficient of friction, so how this model is working here. So the reference is given here, properties modification factor for seismic isolating bearings. So let's just copy it and paste it here and then look into the behavior um, to see why it is discussing this model. And let's just discuss some basic definitions that are included in this uh, theoretical background here. And I will also discuss about the practical approach that is adopted here. I don't think I can visit this link due to weak internet connection. But anyhow, this is a practical implementation of this model. It is basically related to the bearing. So this friction model, this velocity dependent friction model object uh, within OpenSea's environment encapsulates the parameters and behavior of the friction model. It is solely dependent on the velocity, and these are the bearing examples for the base isolators that are given here. So it's likely contains functions and algorithms to calculate friction forces based on velocity and the relevant friction behaviors here. And another discussion is on the material. This is PTFE. So let me just try to open this PTFE material and look at the structure of this material. So uh, tetrafluoroethylene is the nomenclature of this material, and why it is important in the discussion of this OpenSees modeling environment. So this PTFE material it's a synthetic fluoropolymer, and it's commonly known by the brand name Teflon. And this material, uh, it's suitable for applications where the reduced friction is desired, such as bearing seals and coatings, etc. So we have this flare slider bearing element. We have a single friction pendulum bearing elements, and this is the idealization. And look at here. This is a flare sliding. So for flare sliding, the friction will be constant. For the single friction pendulum bearing, the friction will be changing with respect to time. And for the RT Watson EQS bearing element, there will be no friction at what point and maximum friction at other point here. So these are the some of the theoretical background for triple friction pendulum bearing mechanisms, and OpenSeas have incorporated it in its documentation. It is given here, and why it's important to consider the PT FE or PTFE like material on the sliding surfaces. So another thing that is very important here is the stainless steel surface reference. So the stainless steel is a standard example. It's a common material. It's known for its corrosion resistance and strength. So when PTFE slides on stainless steel surface, the interaction between the two materials leads to friction, which this model aims to simulate here. So with this simulation, it's kinetic energy change due to heat it absorbs, and that's why it is categorized here in terms of velocity dependency here. So unlike the simple friction model that assume friction to be constant regardless of the velocity, the velocity dependent friction model considers the fact that friction can change as the relative velocity between the surfaces change, and it is obvious here. Um, this is particularly important for material like the way I discussed here, the PTFE, where friction behavior can vary significantly with the sliding speed. So the reference they have provided here, I wish I can access it. My internet is not so much fast at this moment. I will try to consider it discussing in the other videos. But this is a reference to a specific research paper that is authored by Constantino and others in 1999 for their experimental work. And in this paper presents the experimental data and theoretical analysis on the velocity dependence of friction for PTFE sliding on stainless steel surfaces. So OpenSeas have incorporated there. It's mainly related to the earthquake analysis. So, referencing this paper suggests that the model implemented in OpenSeas is based on the inspiration by the finding and insight presented in the Constantino works in 1999. So, this command that I mentioned create a velocity-dependent friction model. It advocates and tailor for simulating the friction behaviors. So the fact that PTFE that I mentioned here are Teflon, this material here, um, this material basically exhibits significant velocity dependence in its friction behavior, and it's crucial engineering for main two reasons. The first one is the low friction across a range of speeds. And the second most important, which is very, very important, and it is related to the friction model as the self-lubricating properties. So, unlike some materials with friction that increase or decrease significantly with velocity, the PTFE offers a relatively low and stable friction coefficient across a wide range of speeds. And This make it a versatile material for application where consistent low friction is desired and regardless of the operating speed here. So it's quite common in earthquake analysis. And the second thing is the velocity dependence of PTFE is related to its unique molecular structure. It is provided here. So the low surface energy and weak intermolecular force within the PTFE allows surface molecules to readily flow under shear uh, and creating a low friction surface. So this essentially make PTFE self-lubricating behavior, eliminating the need of external lubricants in many cases in its requirement. So these properties make the PTFE reliable in various engineering applications, such as shown here, the bearing and seals, and the sliding components, and one more component that is not related to our discussion, but in electrical application and other non-stick coatings, piping and valves, etc. So our main concern is bearing and seal and sliding components. So that's the most important thing that we should consider. So we need two coefficients of frictions. One coefficient of friction is low, and another coefficient of friction is fast, and then we need a transition state here. So that is given here as well. So this transition state is basically percent of change in the slope here. For example, if we look at this command here, this is the take and point 0.05, it is starting from here and then it's going to 0.163 and then it become constant here based on the finding that they consider here, and the rate is 0.615 at which it is changing at this point here. So it's really important, and the breakaway coefficient is at the room temperature. So if I define it here, for example, if it is 0.05 and 0.163, and transition rate is, for example, zero point 0.6 here. So if I define this model and click on OK, so I have this friction model, and this is discussed in a very detailed way, and this research publication um, in which they have simulated these bearings in this article here. So this is how we define the um, friction model that is velocity dependent here. At the end of these definitions for the friction models, I will do a comparison uh, in a detailed way. And that's how we can define the friction model in the OpenSees. Um, Other than that, I will also discuss about the velocity normal force dependency and velocity pressure dependency and its practical application. So thank you so much for watching.